All right, guys. Well, let's go ahead and take some derivatives of parametric functions today. So that's something you guys have been really curious about, of course. So remember that if we have x of t and y of t for some parametric function, that is a position. So one of the first things that people, of course, want to do when you have a function is take a derivative. So you might think, what does dx dt represent? What does dy dt represent? Well, if we think about this, dx dt would be like a change in the x position, over time. Well, what's a change in position over time? It's a velocity. In particular, you're thinking of a horizontal velocity. Okay. Now, when we think about dy dt, of course, the same thing comes to mind. It's the change in y position over time. So that would represent a vertical velocity. Okay, so let's go ahead and look at just some example problems. So just suppose I tell you that x equals 3t and y equals square root of t plus 2 is the position of something. And let's say the first part of this problem asks us to find the velocity in the x and y directions. And then the second part would be to find the x and y velocity at t equals 2. Okay, so when we think of velocity, so again, this is a position function. We think of velocity, that's saying dx dt, which would just be 3, and my dy dt, so that's, of course, the original one is t plus 2 to the 1/2 power, so that'd be 1/2 times t plus 2 to the negative 1/2, and then by the chain rule, I multiply by 1, which doesn't do anything. Okay, so when I want to find the x and the y velocity at 2, we're saying, okay, what is x prime of 2, and what is y prime of 2? Well, x prime of anything, of course, in this case is just 3, and then y prime of 2 would be 1/2 times 4 to the negative 1/2, which would be 1/2 times 1 over the square root of 4, which is the 1/4. Okay, so that's your x velocity, and that's your y velocity right there. All right, so we can also think about these. We've talked about the vector, the phrasing vector before. Okay, so if you have a position vector, which again, sometimes we write it with like these funky little arrow things. The x of t, y of t is, let's say, I don't know, like t cubed comma sine of 2t. I might ask you to find the velocity vector, and let's go a step further, of course, the acceleration vector. And as you can imagine, acceleration is just the derivative of velocity. So when you're finding those vectors, you're just going to write them in a similar form. A velocity vector is just x prime of t comma y prime of t, and then your acceleration vector is just x double prime of t comma y double prime of t. And just like always, we'll find the velocity before we find the acceleration. Okay, so when I find my velocity, it's just the first derivative, which is 3t squared. The derivative of sine of 2t is cosine of 2t times an extra 2, which we'll just put in front. If we take the acceleration, again, we just take like v prime and, we just take v prime of the x and then v prime of the y. So that just gives us 6t. And then you take the derivative of 2 cosine 2t, so multiply by another 2 and negative, so negative 4 sine of 2t. Okay, so again, you can just use these. These tell you the velocity or the acceleration at any given time of t. Okay, so that's a velocity vector and an acceleration vector. There are some other derivatives, of course, that we are also interested in. So another derivative you might think of is the slope. And the slope of the tangent line, as you might actually expect, is dy dx. Now I want to point out this is a slope. This is not a velocity. Okay. So if we have a graph of like a y versus an x graph for this, and you have some function, I don't know, and then it does something silly like that. If you want to find the slope of the tangent line, like that slope of that purple line right there is dy dx. Now, if you had the dx dt and the dy dt, those don't tell you anything about slope. All those tell you about is they tell you the speed, well, maybe speed's a bad word, so they tell you the velocity at which you're going around the curve. velocity at which you're going around the curve. So the slope is independent of the velocity, right? Like no matter how fast you're going, you could be going around here at 80 miles an hour or 5 miles an hour. The slopes are unchanged. But the velocity just tells you kind of how fast you're going around, where the slope is just like at one point, what's the slope of the tangent line? Okay, now the way that you find dy dx, and you're going to admit this is just brutally genius, is you just find dy dt, and then you divide by dx dt. And you can kind of see in your heart that, oh yeah, bro, the dt's just kind of cancel, and that does make sense. So finding a slope is actually pretty straightforward. So for example, like let's say you have x would be t squared and y would be t cubed minus 3t. If you have to find dy dx, sorry about that, dy dx is just dy dt divided by dx dt. So in this case, dy dt would just be 3t squared minus 3, dx dt would just be 2t. If it asks you in another example to say, using the same equation, what is the tangent line, right, the tangent line at t equals 2? Okay, now, so again, we're using the same set of equations that we see right here. Anytime we're writing a tangent line, we need to find a point, and we need to find the slope. And in this case, that slope is the dy dx. So the dy dx at t equals 2 would be 3 times 2 squared minus 3 over 2 times 2. So that's 12 minus 3, that's 9 over 4. If you want to find the point at t equals 2, that's just the position. So if you had the position, x would just be 2 squared, which is 4. Your y would just be 2 cubed minus 3 times 2, which is 2. So your tangent line would actually just look like y minus 2 equals 9/4 times x minus 4. Okay, so that's how you would find a tangent line. Okay, the other thing we might want to talk about, and we've seen some problems like this before, is a horizontal tangent versus a vertical tangent. Okay, now, a horizontal tangent, as you guys may remember, that means that you have a slope that is equal to 0. Now, in terms of parametric, what that means is, okay, so you have the dy dt divided by your dx dt, because that's what your dy dx is. Jeez. And that's equal to 0. If you have a fraction equal to 0, that means the top is equal to 0. That means dy dt is equal to 0, which actually makes sense, because at that one point right there, the y is not changing. As you were to go around that curve, the x is changing, but the y itself is not changing. If you were to have a vertical tangent, what that would mean is, okay, well, at a vertical tangent, my slope, my dy dx, is undefined, which is something over 0, right? When you divide by 0, that's undefined. So when you set that up, what that means is your dx dt is equal to 0. Okay, so for example, let's say we have, I don't know, the problem x equals t squared. Let's just use the same equation. And then y equals t cubed minus 3t. And I might ask you to, I don't know, find the point on the curve, or the points on the curve, where this has a horizontal tangent. Okay, so again, let's think through this process. What does a horizontal tangent mean? So I draw the picture in my head. I don't like have this memorized or anything. I draw the picture in my head. Okay, it means I have a slope of 0. So my slope's equal to 0. It means the top's equal to 0. So my dy dt is equal to 0. Okay, so that means that 3t squared minus 3 equals 0. So 3 times t squared minus 1 equals 0. All right, so that means my t is 1 or my t is negative 1. Now let's make sure we finish the problem. If we're asking for points on a curve, it's always asking for x and y. So what I need to do then is just plug these in so that we can find those x values and the y values. Okay, so when t is equal to 1, let's just go back to these equations for x and y. When t is equal to 1, my x is equal to 1 squared, my y is equal to 1 cubed minus 3 times 1. So that just gives me the point 1 comma negative 2. when t is -1, I have x is equal to -1 squared is still 1, y is -1 cubed minus 3 times -1. I don't know, it's like -1 plus 3 or something, so that's -2. Oh, it's the same point? Oh, that's kind of weird. Okay, so it's still just the point 1 comma -2. Oh, that's +2. Yeah, I'm dumb. All right, so those are the 2 points. Now, I'm not going to do it, of course, but if you had a vertical tangent, you would follow the same thing. Right, a vertical tangent, that would be where, you're like that, so that's like where your dx dt is equal to 0. All right, and then you do the same process. Okay, one last derivative that I wanted to share with you in this video, concavity. Okay, concavity, the second derivative of y with respect to x. Now, you can kind of see this from the notation, but this is sadly not just taking the second derivative of y divided by the second derivative of x. You can see, you can see in this case that doesn't work because of the dx squared, not a d squared x. So this approach isn't going to work. So what we need is another approach, and this is going to seem a little weird because it's actually asymmetrical. But what is concavity? Well, it is the derivative of the slope. So it's saying let's take the derivative of dy dx. So what that's saying is let's take the derivative of dy dx with respect to x. So in terms of parametric, in terms of t, it's saying let's take the derivative of the slope in terms of t, and then take the derivative of x in terms of t, and divide those. So that's how we actually find the concavity. And some of these, of course, get pretty hairy. But so what you're doing is you're taking the derivative of the slope and you're dividing by dx dt. That's how you find a concavity. And again, we're kind of clued in by the notation. So just for an example, if I tell you x equals 2t plus 3 and y is equal to 6t cubed plus 2t squared minus 3, and I'm going to ask you to find the d squared y dx squared, this concavity. And again, these are a little hairy, but the thought process is to use this equation. We just take the derivative of the slope, dy dx, and divide by the dx dt. Okay, so let's see. The slope is equal to dy dx. And we can do that very quickly. That's 18t squared plus 4t minus 0. The dx dt is just 2, right? I just did right here dy dt over dx dt. Okay, so I could write this out a little further, right? That's just 9t squared plus 2t. So when I want to find the concavity, that's equal to, let's take the derivative of the slope, and then let's divide by the dx dt, which luckily we just had. So here's my slope. I'll take the derivative of that slope. So that gives me, let's see, 18t plus 2. And the dx dt, I actually already found that, or I can very quickly, again, it's just 2. So if I wanted, I could simplify it to 9t plus 1. These get messy with a lot of equations, but just the general idea is thinking, okay, I'm just finding the derivative of the slope with respect to x, right? Because that's what the concavity is. It's the derivative of the slope with respect to x. I'm going to write that abbreviation out because you probably don't know. With respect to x. And that's how you want to think about these problems. Okay, my friends, thank you so much for watching. Bring me some questions to class. I'll see you guys soon.